Okay, we're going to look now at some different ways we classify and quantify streams. One of those is whether or not the water is flowing year-round. So a stream that is perennial is a permanent stream, and it is going to have water in the channel year-round. It has water in the channel year-round, like even when it's not raining, because it is sustained by the groundwater. So groundwater flow keeps water in the stream. An ephemeral stream is a stream that is only going to flow during a season where there is a lot of rain, or maybe just after a rain event. That is because the stream channel is above the water table. The water table we'll learn about more in our groundwater chapter. It is the top of the saturated zone, the top of the area underground that is full of water. So if the stream is touching the water table, then it is perennial and will flow year-round. If the stream channel is above the water table, there will be times perhaps when there is no flow. And in general, we think of perennial and ephemeral streams as being perennial east of the Mississippi and ephemeral west of the Mississippi. This isn't true for every stream, but in general, that's what we think of, the way we think of that. The way we talk about the amount of water flowing down a stream is using the term discharge, and we use a variable Q in equations to show discharge. So it's the amount of water flowing down the stream over time. The amount is the volume, and we would measure that in feet cubed, so cubes of water with a foot on each side, and we would measure the time in seconds. We then multiply feet cubed times feet times feet times feet and get feet cubed. So that gives us the volume, and divide it by seconds. Then we would read it as cubic feet per second. So the abbreviation that's commonly used is this one here, CFS. We can also use meters, so it would be meters cubed per second, or CMS, cubic meters per second. That's difficult to measure, cubes of water. So we often will measure the velocity of water and multiply that times the area to get discharge. So take a look here. Velocity would be in feet per second, just like your car is in miles per hour, a length divided by a time. This would be feet divided by seconds. And then that is times feet squared. So it's an area would be a squared unit, and then we multiply feet times feet squared, add those exponents and get feet cubed divided by seconds, CFS. We can do that also with meters. And this time doesn't always have to be seconds. We can change that as well, but it's usually given as seconds. So how big is that stream? It's all about the velocity and the discharge. So here's that cube of water. This is what a measuring station would look like, where we're measuring the width of the stream, the depth of the stream, and the velocity with this propeller. And then we would make a calculation of the area times the velocity to get the discharge. All right, if the area decreases, so we take our channel and make it smaller, what would happen to the velocity? Would it increase, decrease, independent, or I just want to know if I can tube it? So the answer there is the velocity would increase if we decrease the channel size and the discharge stayed the same. All right, channel morphology. Morphology is just a fancy word term to talk about shape. So a stream channel can be like this top one here that's almost like a half a cylinder. The wetted perimeter of that, the length of all this wet area would be 19 meters, the depth 6 meters. So it's pretty shallow and not very wide. If we were to take that stream and flatten it out so that it's now 30 meters wide and 2 meters depth, the wetted perimeter is now not quite double, but 32 meters. But we still have the same area of the stream. So you can change up the velocity in this area here, 57 meters squared. The fastest flow is in the center of the channel. When straight, that's pretty rare in nature to have like a really perfectly half a cylinder straight flowing stream. In this image here, the larger wetted perimeter, the same area, is going to have a slower flow spread out over that larger wetted perimeter. There's going to be more friction with the channel in that bottom image. Flow, like I said, straight, just linear flow is not very common. Normally, you're going to have a stream with eddies, that water is actually going to flow backwards, it's going to swirl, there'll be little whirlpools, there's going to be sediment in the stream. So laminar flow is not very common. What's really more common is this turbulent flow. Turbulence is going to cause then those eddies and whirlpools and swirls. Over time, that can cause erosion. So this is an image of what we call potholes, where this bedrock had erosion and a rock or maybe some sand got in there, and over many, many, many years, hundreds or thousands of years, it scoured out these rounded areas with a whirlpool of an abrasion of that loose sediment against the bedrock. All right. So in the stream channel, this is obviously brown, it's high flow, there's movement of sediment. So the stream is going to pick up sediment and that is erosion and transport it, and then eventually that sediment is going to fall out of suspension, and that is deposition. Alluvium is the term here that is sediment deposited by streams. And the deposition of the sediment is going to be mostly dependent on like what size is that sediment, and then what is the velocity of the water. There's also a term, base level, and base level is going to help determine the gradient of the stream. And so if the gradient of the stream changes, then the erosive power is going to change as well. There are two terms that describe the size and the volume of sediment that the stream can carry, and that's competency, that's particle size, and capacity is the total load. What's the volume that the stream can carry? That load is a combination of different loads. The bed load along the bottom of the stream, the suspended load suspended up in the channel, and then there is the dissolved load that is ions. And so capacity is going to depend on what is the Q, or remember that was discharge, and what is the competency, that largest size that can be carried. Here's a look at the different loads. Move my face out of the way. So a normal bed load is we call this saltation, the bouncing and rolling of boulders and gravel along the bottom. This moves during the flood, is this brown area in here that can for sure move, but it takes high water to get it moving. And then the substrate would just be what doesn't move in the channel, maybe bedrock or some kind of, just old sediments that are compacted and pretty stuck together. So the saltating load, and then there is the suspended load. Most of the suspended load is going to be pretty fine grained, something like a clay. Those clay particles will swirl up into the water column and stay for some long amount of time. The dissolved ones are cations and anions that are floating down the stream that are dissolved from the bedrock. So the total load is that bed load plus the dissolved load, whatever cations and anions have washed from the watershed, and then the suspended load. The movement of the solid particles is dependent on their size. So this diagram is called the Holmstrom diagram. And the Holmstrom diagram, on the y-axis is the velocity, and on the x-axis is the grain size. So over here we have cobbles and boulders. It takes a lot of velocity to get those particles to move. That is going to drop down until we get to a sand. So right now, just pay attention to the left side of the graph. Ignore that right side. So on the left side, we have velocity dropping as grain size drops. Then, okay, now look at the right side. It's weird. It goes up again. And why does it go up? It goes up because clay tends to stick to itself. It's actually a bit of a charged particle, and so clay sticks to itself, it sticks to water, it's cohesive. And so when it does that, it's hard to get it to move. And so it takes a higher velocity to get these cohesive clays and silts to move than it does a non-cohesive clay and silt. Once it's moving, though, it stays moving. Here's the image of those clay particles. They have a bit of a charge to them, and so they're cohesive, they stick together.